Hi everyone, so this is going to be a video about a linear algebra problem that has to do with transformations and coordinates. It goes like this: let the basis beta equal these three vectors v1, v2, and v3, and let the transformation from R3 be a linear function so that each of these vectors are transformed in this way, tv1, tv2, and tv3. And part of the question goes as follows: find the coordinates of t of v3 relative to the basis beta. So basically what that's saying is it wants you to find tv3, and we're going to put it in brackets to show that we want it relative to beta. Alright, so basically to find these coordinates, we're going to take the basis and rewrite it as a matrix right here. And we're going to make it an augmented matrix with T of V3, which, if we look at the problem, was 1, 0, 0. So there's your augmented matrix. So what you do is you simply just put it in reduced row echelon form. Alright, and there's calculators online for how to do that, or you can look up the manual way to do it. That's not the focus of this video, so I'm just going to assume that you know how to do that and you understand what's going on. Because the video would probably double in length if I went through all of those steps. But this is what you get. You get negative 1, 1/2, and 1 on this side of the augmented matrix. This, of course, is going to be our reduced row echelon form. So this right here is actually your answer to this part of the problem, part A. So those are your coordinates, and it's really just a matter of putting your basis in one side of the augmented matrix and your vector on the other side, putting it in reduced row echelon form, and whatever is on this side is your answer. Alright, so let's look at part B. Let's go ahead and look at part B. Okay. Part B is find the matrix of T relative to the basis beta. So now, instead of, whereas before we were finding just a just one of these, just one of the vectors of the T transformation, now what we're going to be doing is finding the entire matrix. So that's written like that. And basically a way to understand it is it's equal to it's going to be a matrix that's just the conjunction of basically each of the vectors that we did in part A. Like we did T of V3. Sorry, I'm trying to hold this paper down while I have a camera in one hand. Okay. Does that make sense? So what we did in part A is we found this. Well, now we're trying to find this, and it's just each of the T of V1, T of V2, and T of V3 together in a matrix. So now we could do what we did in part A, and we could do it the exact same way. Completely legal. And because we remember from part A we got this. But we can also use just inspection. The nice thing about this is if you look at so let's look at T of V1. It is negative 1, 1, 0. Up here in the basis, this is actually also the same thing. Do you see that? So we can write T of V1 relative to the basis as literally just V3 in the basis. This is just like a sub-step. We're going to solve this by inspection. instead of the other way, which always works too, which was done in part A. So then we can look at T of V2, and also it's going to have to do with inspection. So T of V2, negative 422. This is actually a scalar multiple of V1. If you multiply each of these by 2, you get negative 422. So basically you can write that as like so. And then we know that this was just negative 1/2, 1. So when we're writing this out, it's just going to be, we'll fill out the one that we know already. So you have your last column. We know that it's this. But what does it mean to write V of 3? I don't know. Maybe you could just understand the pattern here. V3 is the third one, so I'm going to write 0, 0, 1. V3 would be the last number in this. Like this is V1, V2, V3. And it's just multiplied by a scalar of 1. So it's just going to be 1. Whereas for equals 2 V1, we're going to want to write it like that, because V1 is right here, V2, V3. But it's a scalar of 2, so 2 right here. And that's just your whole entire matrix T relative to the basis. That's your answer for part B. Okay? And then finally, for part C, find the standard matrix of T. So what is your standard matrix of T? So it's written like that. And basically what it can do is you can just multiply, you're going to be able to multiply the vector and the basis by this standard matrix, and you get the transformed vector out of it for each of them. You multiply again for each of them. That's all the standard matrix is, or at least that's the way to understand it for this problem. So it's important to remember that there's a formula that is like this. This is just a formula in linear algebra. You can it might help, but P is just the matrix whose columns are the standard coordinates of beta, of the basis. Sorry, this is supposed to be. We found that, so that's what P is, but you can also, here I'll just write it out. It is going to be, because remember, right here we have each of these. Negative 2, 1, 1, 0, 0, 2, negative 1, 1, 0. That's going to be your column vectors for the matrix. And then to get the inverse, because you need that for this formula, basically what you would do is you would set up the augmented matrix. If you want to do it by hand, you would set up the augmented matrix where you have this on the left side and you would have the identity matrix on the right side, and you would just reduce row echelon form this, and whatever you have on the right side is going to be your inverse. And what you get from that is you can also use a calculator, online calculator, MATLAB. There's a number of ways to do it, but here's the result. This is all you need to know for this video. All right, so we have all of the parts of this equation now, right here, because remember in part B we solved for T relative to beta, and it was this. Sorry, my camera is not focusing well at all. We'll just continue. So you can write that all out as matrix multiplication. That entire formula. Sorry. Alright, and you basically just do matrix multiplication across all of those, and you get 0, 1, God. Ignore that. You would get 0, 1, -2, 0, 0, 1, 1, 1, 1. And that's going to be your standard matrix. And you can check that this is right by, again, multiplying any of these. It could be V1, V2, V3, but this will be true for each of them. Alright, so that is a 3-part problem from linear algebra involving transformations and coordinates. I hope that helped a little bit. I know it wasn't very well organized and the camera was shaky the entire time, but that's the best I got for now. Thanks.